Hello students, this is the third in the 4-video series on ICE charts. This ICE chart is probably going to consist of the hardest sorts of skills that you're going to need to do in order to solve it. So feel free to stop the video and write down the question that's below or that is on your screen. Anytime you want to pause the video to try to do some of the work ahead of time or to do all the work ahead of time, that would be great. By the end of this video, you'll have all the answers to all of these questions. So let's get going. So the problem starts off with just names. And so before we even get to part A, we're really going to have to write formulas for these compounds. So, lead 2 nitrate. The symbol for lead is Pb, and this 2 is the charge on lead, and then nitrate is NO3, and its charge is 1 minus. So to get those two even, you're going to have to write Pb NO3 2. And aluminum chloride is a little easier. Aluminum's charge Al3 plus, and then chloride is 1 minus. So now we need 3 chlorides here. So the formula for this is AlCl3. Now, the question, part A, says to write the correct formula and the correct name of the products of the reaction. Well, what we know is that when lead nitrate and aluminum chloride react, the parts are all just floating around in solution. So what we want to do is we want to just write the parts down, and I'll put out like a little tic-tac-toe board, or some people call it a Punnett square. But if we've already written the parts here, now we can put the parts in this to predict the products. So we pick any one and we put it up here. This box is going to remain empty. So we're going to put lead in this one, and then what is with lead over here? Well, nitrate, NO3, 1 minus. Now realize that NO3 1 minus, we don't put the 2 there because that just comes from how many we need to make sure the charges cancel out. We just have a whole bunch of lead ions and a whole bunch of nitrate ions, and we're not going to care how many there are. Okay, now we do the same thing with aluminum. We're going to put Al3 plus here, and then we're going to put Cl 1 minus here, and we're not going to care that we have 3 of them there. Okay, we're just gonna have a whole bunch of chloride ions floating around. Now, what I like about this chart is that we can use this to figure out what's going to come together. What we know is that opposites attract. So aluminum is a plus charge and lead is a plus charge. 2 plus charges are not going to come together, so we're not going to have any product there. And then the same is true for chlorine and nitrate. Chlorine is a negative, nitrate is a negative, and so we're going to have nothing coming together there. Okay. What can end up happening, though, is the lead can be attracted to the chlorine. And so what ends up happening is we have to write the formula based solely on the charge. So if this is Pb 2 plus and lead and chlorine 1 minus, that means that we need 2 chlorines in the compound. So this is going to be PbCl2, lead, and so that's that. And now the same is going to be true for aluminum. If we have aluminum, we have a 3 plus charge. It comes together with nitrate. Just so you know, it's 9 o'clock. And so we need to put 3 nitrates there because we need to have the charges cancel each other out. Al NO3, and we're going to put that in parentheses, and we'll put 3. So those are our 2 products. the formulas of our two products. But now we want to name them. So part A says, give me the formula and give me a name. Okay, well, let's see. Actually, it becomes pretty straightforward when when we already have the name here. We can kind of just jumble it up and figure it out. We can just go lead 2 chloride and aluminum nitrate, and that's it. But let's go through PbCl2. Okay, so this one here is going to be, I'll move it up a little. Okay, so this one here is going to be, let's see, here, I'll get this there. Let's just do this. PbCl2. Okay, this is a transition metal. So if it's a transition metal, we need to put its charge. So that's going to be lead. Well, we don't know its charge yet, but chlorine we do know. Chloride, and its charge is 1-. There's 2 of them. There's only 1 of these, so this must be lead 2 chloride. And then AlNO3. This is aluminum. Aluminum's not a transition metal. So because it's not a transition metal, all we have to do is name the 2 parts. Aluminum, and this is nitrate. So that's part A. So you can see that I kind of paused the video for a second. What I wanted to do is give you a chance to write and balance your own equation. So you can pause it right now if you need to. I'm going to bring in the balanced chemical equation with all the molar masses and the starting material and the ICE chart already set up. So let's take a look at how this is going on. Okay, so there we go. Okay, there's everything done and balanced. Okay, now we have to, first things first, we have to convert to moles. So when we convert to moles, we have to X-line. Okay, so it's 3.69 grams. Okay, I'm going to show you an example problem down here. 3.69 grams of lead 2 nitrate, and we're going to X-line it, and we're going to use, let's see, we want to get rid of grams, so we're going to put grams on the bottom, moles on the top. For every 1 mole, it's 345 grams, and when we do that math, it's going to equal 0.0107 moles. Okay, so we can put that 0.0107 right up in that box. Now, you can do the same thing, and this is what I've been trying to say all along, is that the pattern is going to be the same. Instead of lead nitrate here, you're going to put aluminum chloride's numbers. Okay, so when you do that, and I'm not going to show you this X line, take a minute, try it yourself. Okay, you can pause the video, and you get 0.0361 as your initial number of moles. Now, when we calculate the limiting reactant, remember we have to take the one that is present in the least amount stoichiometrically. Now, I picked this problem because I wanted to show you that there are certain shortcuts that you can make. Okay, now, if you have some math sense, what you can do is you can take this and you divide it by 3 and you get some number definitely a lot less than 0.01. Now this number divided by 2, which is that coefficient, is definitely not even going to be smaller than that number, let alone this number divided by 3. So I already know that this is going to be my limiting reactant. And so because that is my limiting reactant, that is the thing that is going to go down to 0 at the very end. Now you can take this and you can subtract. Let me try to get that focused again. Okay, so 0.0107 moles. Okay, and that's how we get it to 0. Now, to convert from, and this is the most important box, to convert from, to get us from this box to this box, and then to this box, and then to this box, we have to use the balanced chemical equation. I'm going to show you a little bit how to do that. I'm going to show you one example. Okay, and so when you do that, And we have 0.0107 moles of lead 2 nitrate, NO3 2. And then we're going to X-line it, but now instead of getting rid of moles, as this focuses, we're trying to get rid of lead 2 nitrate. So we're going to put lead 2 nitrate on the bottom, and we're going to put the thing that we are converting on the top. In this case, it's going to be aluminum chloride, AlCl3. And then we're going to use the coefficients, the balanced chemical equation. And the coefficient for that is 2. The coefficient for that is 3. And then we do the math. Notice the lead nitrate cancels, and we get 0.00713. And in this case, it's moles of aluminum chloride. Al, look, we have moles. Sorry, I didn't mean to cancel that. The AlCl3. And so that value can go right here, 0.00713. Now, I also chose this because it shows you some other chemical shortcuts that you can take. Okay, look, the chemical ratio here, the stoichiometric ratio of this to this is 3 to 3, or 1 to 1. For every one of these that you use, you make one of these. It's a 1 to 1 ratio. So if we're going to use up 0.0107 moles of this, we can make 0.0107 moles of that. It's a very strict, very simple shortcut that we can take. Okay, we can have the chemistry help us do the math. And now, again, we can look and we can have the chemistry help us. Here's a 2 and a 2. It's a 1 to 1 ratio. For every one of these made, or sorry, for every one of these used up, we make one of these. For every 2 of these, we would make 2 of those. If we had 14 of these, we would make 14 of those. So if we're using up 0.00713 moles, we can make 0.0713 moles. So we can do some shortcuts like that to help us out. Now, super straightforward. Now we have filled out almost all of our IC chart. Now we do some of the basic math. We go 0.0107 moles, 0.00713 moles, and then we subtract these two, and you get 0.0290 moles. Right, okay. You have to keep 3 significant figures, so that's always the hard part, is keeping 3 sig figs. Okay, maybe not the hard part, but the part that you have to make sure you remember. Now it's just a matter of converting back to grams. The problem asked, how many grams of everything do you have? We've actually solved, based on this, we've determined the limiting reagent, we've determined how many initial number of moles we have, and then we've determined how many moles of product we have. Now we need to determine how many grams of leftover stuff. Now this one is obviously going to be 0 grams. I'll do that one in my head. Okay, but now let's do a sample problem for this. Okay, let's do aluminum chloride. Okay, so for aluminum chloride, you have 0.0290 moles of aluminum chloride left over. We're going to X-line it. Now in this case, we want to get rid of moles, so we're going to put moles on the bottom and grams on the top. For every 1 mole, and we have the molar mass, 1 mole weighs 133.35 grams. And so now we do the math, and I'm going to double check my own math that I started with, and I have, let me see if I can get this to focus. Okay, so we do 0.0290 times 133.35, and when we do that, we get 3.87 grams. Okay, so now back here, okay, we do 3.87 grams. We do the same thing using each compound's molar mass. We X-line it, and so when we do that, we get 2. 0.97 grams here. And then for this one, we also get 1.52 grams for that one. Okay. And then we can double check this, and you will see that yes, when you add these up using conservation of the conservation of matter, conservation of mass, when you add those up, you get 8.51. And then when you take these masses up and you add those, you will get 8.36. Now these two are further apart than some of the other examples we've done, but it's still acceptable for me because I know I did this right, and so that is that. Now there's one more part to this question that we have to answer, and that's a percent yield. So I'm going to take a moment and show you how to do percent yield. Okay. The problem asks us to calculate the percent yield if we have 2.17 grams of the lead compound. Now, going back to our ICE chart, the point is that this is the lead compound that we're talking about. So this value right here is what we call the theoretical yield. So what we can do is we can take and we can almost calculate our score here. That's what a percent yield is. It's basically saying how good did we do. So this is our actual yield. This tells us how much we made if we were to go into the lab. That's how much that we got on our filter paper, that we dried, that we weighed. Okay? So to calculate the percent yield, all you have to do is you have to take the actual yield, put it over the theoretical yield, and multiply by 100. So in this case, our actual yield is 2.17 grams. Our theoretical yield from our ICE chart was 2.97 grams. And we multiply that by 100, and we're going to get 73.1%. Now, a couple side notes about yield. Just know that you must compare units that are in the same number. So you can't compare grams to moles, or moles to grams, or liters to grams. Typically you compare gram to gram. And lastly, when you have a yield, this number doesn't mean that you're doing bad or good. You don't know the chemistry well enough to know that if a 73.1% yield is good or bad. So just know you report whatever number you get. So 73.1% is the percent yield.